Hello, my name is Alex Weaver, and I'll be presenting the paper Contention Resolution with Predictions, written with Seth Gilbert, Cal Newport, and Nitin Vaidya. So in this paper, we study the contention resolution problem under the assumption that the nodes are provided some advanced knowledge of the network size. So we won't give the nodes the explicit network size, but we will model this knowledge as a probability distribution over the possible network sizes. And then we produce upper bounds and lower bounds with respect to the Shannon entropy of this distribution. So the contention resolution problem, which we study in this paper, consists of a complete network of nodes where time proceeds in synchronized rounds. In each round, nodes can choose whether to broadcast or to stay silent, and the goal of the problem is to have a round in which exactly one node broadcasts. So there are two variations of this problem, and they depend on whether or not nodes can detect what are called collisions. So a collision describes the event that more than one node broadcasts in a given round. So in both variations of this problem, some number of nodes broadcast, and then after which the nodes can observe something about how many nodes broadcasted. So in the case without collision detection, all the nodes are able to detect is whether or not exactly one node broadcasted in the round. In contrast to the setting with collision detection, the nodes can distinguish between the events that no nodes broadcasted and the event that there was a collision. And it's worth noting that what we study in this paper is called strong collision detection, where even the nodes that cause the collision, the ones that broadcasted in the round, are informed of the fact that there was a collision. The types of algorithms that we'll study in this paper are called uniform algorithms, and this describes the property that each node is given the same set of broadcast probabilities to use in every round. So which broadcast probability the node uses depends on the sequence of observations made up into that point. So in the case without collision detection, the only observation that the nodes can make until the problem is solved is that it was not the case that exactly one node broadcasted in the previous round. Otherwise, the problem would be resolved and the algorithm would terminate. Therefore, we can represent an algorithm, a uniform algorithm for the setting without collision detection as a sequence of probabilities. In contrast, for the setting with collision detection, we represent algorithms as a binary tree of probabilities. And this is because nodes can detect one of two events in each round that contention resolution is not resolved, either that no nodes broadcasted or that there was a collision in the previous round. And using the sequence of observations, the nodes can traverse this binary tree and determine which broadcast probability to use in each round. So this problem in both variations is well studied for the general setting. And in both cases, we have these tight bounds that hold an expectation. So for the setting without collision detection, this bound is order log n rounds in expectation. And for the case with collision detection, this bound is reduced to log n rounds in expectation. So in our work, we're not so concerned with the general setting. Instead, we want to ask this question of, can we achieve some speed up if the nodes are provided some advanced knowledge of the network? In particular, we're interested in this knowledge being about the size of the network. So why might this matter? Well, if we are in the extreme scenario where we specifically give the nodes the size of the network, then we know we can solve this problem very quickly. In fact, we could solve it in a constant number of rounds in expectation. And what's more, this bound can be achieved fairly simply by having each node broadcast in every round with probability 1 over the size of the network. So while we have these two extremes here, where we have no knowledge about the network ahead of time, being well studied, and this bound of perfect knowledge being provided being somewhat straightforward, the space in between is relatively unexplored, and this is where our work comes in. So we're interested in the setting where the nodes are provided some knowledge of the network size that is neither perfect, but does not force them to start from scratch either. So what do we mean by imperfect knowledge, and where might this imperfect knowledge come from? Well, we can imagine that in practice, what we have is a network of nodes that have been running for some time, and they are collecting observations about the network state and feeding them into a machine learning algorithm where which they're using to build a stochastic knowledge of the network size. And so then we can imagine what the algorithm might produce is then a probability distribution over the possible network sizes. And this might take the form of a single distribution, or it could be an evolving distribution that the nodes are constantly updating as more information becomes available. In either case, this treatment of the knowledge of the network size as a probability distribution is useful because it allows us to generalize between the extremes we saw earlier. So on the left here, we have the perfect knowledge setting, which is modeled by the point distribution, where the nodes know exactly which network size is accurate. In contrast, on the right, with the uniform distribution, the nodes don't have comparatively little knowledge about the size of the network, with all sizes being equally likely. However, in practice, we can imagine what the machine learning model will give us is something in between these two, where there's a few estimates that are given higher weight than others, but no perfect knowledge is provided. So what we're missing for the purposes of this paper is a way to quantify this relationship. So again, on the left with the point distribution, where perfect knowledge is available, our contention resolution problem is very easy to solve. And on the right with the uniform distribution, it seems more difficult to solve the contention resolution problem since we don't have very much knowledge about which size estimate is true. So we either have to use a general algorithm for contention resolution, or we have to try each of these network sizes. So we need some metric which can capture this relationship. And it turns out that Shannon entropy does just this. So Shannon entropy gives us a value that corresponds to how difficult it will be to solve the contention resolution problem, as we show, taking as input the size distribution of the network. So we see it's nice because it provides a lower value for something like the point distribution, and it is higher for something like the uniform distribution. In fact, for the uniform distribution, this will correspond to the highest possible entropy possible. So if we have a distribution of n values, the highest entropy we can expect from this distribution corresponding to the uniform distribution is log n for n values. One last thing to note before we can display our results is that we actually don't produce bounds with respect to the Shannon entropy of the true network size distribution, or the original network size distribution, which we denote x here. And the reason for that is we actually don't need to land on the actual size of the network in order to solve the problem quickly. In fact, it's totally fine for us to be within a constant factor of the actual network size. So for this reason, we can aggregate the network size estimates into log n buckets, where each bucket contains twice as many estimates as the bucket before it, such that all estimates within the same bucket are within a constant factor of each other. And so we get this aggregated distribution of log n values, which turns out to be just as useful to solving the contention resolution problem. So then we will express our bounds with respect to the Shannon entropy of this condensed distribution, which we denote h of c of x. And it's again worth noting that since there are log n values to this distribution, the worst case entropy is going to be log n, again corresponding to the uniform distribution. So we're finally ready to take a look at the bounds that we produce in this paper. And again, we produce both lower and upper bounds for both variants of the problem. However, at first glance, these bounds can be a little bit difficult to parse. So what we can do is we can substitute in this worst case entropy for the condensed size distribution of log n to get some more readable and more comparable bounds. So then we get something like this. So again, this corresponds to the worst case entropy of the condensed size distribution, which is log n, corresponding to the uniform distribution. And the thing to note here is that our lower bounds, even plugging in the worst case Shannon entropy, are relatively close to the existing lower bounds. And what's interesting to note about this is, one, that we use an entirely different technique for deriving these bounds, using this novel connection between the entropy and contention resolution. And two, that our bounds, like our upper bounds, improve with the entropy decreasing. So if we have a lower Shannon entropy of the condensed distribution, then we will achieve a faster bound. So I'll use my remaining time to dig into one of these lower bounds, as it really illustrates this clear connection that we develop between the contention resolution problem and the Shannon entropy, which is the lower bound for the no collision detection setting. So in the paper, this is done in 2 steps. The first step, we will reduce contention resolution to range finding, which, as you'll see, has a very simple intuition behind it. And the second step is we reduce this range finding problem to the problem of information coding. And we'll focus more on the second step, as it really illustrates where this dependency on the Shannon entropy comes in. But in order to do either of these steps, we have to introduce both the range finding and the information coding problems. So let's start with range finding. So for range finding, we'll draw a value v at random from some distribution. And our goal is to find a value within a certain range of v. So within this distance, capital D of v, which is fixed. And so then a solution to the range finding problem takes the form of a sequence S of values plotted here. And so we'll say the sequence S solves this particular instance of the range finding problem in t steps if the tth element falls within distance d of v. So that's range finding. So while we introduce range finding as it's sort of a more abstract problem to help with our reduction, information coding, by contrast, is a very well-established and well-studied problem. It describes a setting where we're given an alphabet of characters, and each character or symbol has some probability of occurring. And the goal is to develop a coding scheme where we assign codes to these symbols in such a way that we minimize the expected length of the code of the encoded characters. So in order to do that, we assign shorter codes to the symbols that are more frequent, such as B in this example here. And a very useful result from this field is the source code theorem, which gives us a tight bound on the expected code length for any coding scheme, which is the Shannon entropy of the distribution which the symbols are drawn from. And we'll use this result several times in our paper. So now that we've introduced both problems, let's talk about our reduction. So we'll start from contention resolution to range finding. And like I said, this is the more intuitive one to understand, since we, again, our uniform algorithm for the no collision detection setting takes the form as simply a sequence of probabilities. And we can imagine each of these probabilities as corresponding to some imagined estimate of the network size. And therefore, it's very easy to envision transforming the sequence of probabilities into a sequence of values, which then looks like a solution to a range finding problem, as pictured here. So we take our contention resolution algorithm A and generate this range finding sequence S of A. And then we'll now do the second step of our reduction, which is to reduce this range finding sequence to a coding scheme, and actually use this sequence S to allow Alice and Bob to send an encoded message to each other. So in this example, Alice and Bob start with the same range finding sequence S, and Alice is going to draw a value randomly and try to encode it using S and send it to Bob. And she chooses her target value randomly, and she looks at her sequence S and finds the first element in S, which falls within this distance capital D of the target value. And she'll make a note of 2 things. She'll first make a note of the index of this element, which is little t. And then she'll make a note of the actual distance between the selected element and the target value v, which we denote little d here. So she'll make a note of both td, and she will send this pair to Bob. And so now Bob, who also has the same copy of S, receives this pair from Alice and uses it to decode Alice's value by tracking down the tth element of the sequence and then traversing the extra distance d to the target value, and therefore arriving at Alice's original value, v. It's worth noting that in practice, we might need an extra bit to denote the sign of the distance, so Bob knows which direction to move in, but that's not as important for capturing the intuition here. So now we can analyze the length of the code that Alice needs to send to Bob, this pair TD. And so obviously this code is given length log T plus log D bits, where capital D is obviously an upper bound on the distance little d. And T is the interesting part here, is a random variable, which describes how many steps Alice has to look at to find a value within this distance capital D of the target value V to encode and send to Bob. And so then what we have by the source code theorem is that the expected length of this code is lower bounded by the entropy of the distribution we draw from, in this case, the condensed size distribution. So combining these two facts and using some algebra and relying on Jensen's inequality, we can show that we can lower bound the expected value of T, which again is the complexity of the range finding sequence, which is how many steps Alice has to look through to find a suitable value to encode. So we can show that the expected value of T is lower bounded by 2 to the entropy of the condensed distribution over this fixed distance D. So to complete our proof, we'll have to remember, where does this solution that they're using to encode come from, the sequence S? Well, recall that we transformed a contention resolution algorithm A, which is just a sequence of probabilities, into a range finding sequence S. And this sequence S is what we use to encode the values between Alice and Bob. So in our paper, we prove this fact about our reduction, which is that if we set D to be order log n, then we can prove the following, which is that if we have a contention resolution algorithm that solves the problem for C of X and T rounds in expectation, then for this fixed distance D of order log n, we can map it to a sequence S of A, which solves range finding and at most 2T rounds in expectation. So then this allows us to use our lower bound on the range finding complexity that we showed previously to find a lower bound on the contention resolution complexity. And they are within a constant factor of each other. And so if we plug in this value for D, then this arrives at our lower bound, which we showed earlier. And so that's the full intuition behind how we capture this lower bound here. And so as we're wrapping up, what's important to note about what we just talked about is that we proved more or less the same lower bound that already exists, but using this totally new technique and this very novel connection we make between the contention resolution problem and the Shannon entropy. What we didn't talk about here are our upper bounds, where we use this connection once again, in many cases taking optimal information codes and using them to develop contention resolution algorithms to create our upper bounds. Another thing we don't talk about is we prove in our paper our ability to develop these algorithms using a distribution that actually is not the true size distribution. So we allow the distribution used by the algorithm to be some distance away from the true distribution. And then we present time complexity bounds that rely on both the Shannon entropy of the true distribution and this distance from the distribution used by the participants. And lastly, we study the setting of perfect advice, meaning we are not so concerned with the structure of the advice given to the nodes. If we imagine this presentation, the advice given is the distribution over the network sizes. Instead, we're allowed to give any advice we want, but we're limited on the number of bits we can send. So obviously, if the number of bits is allowed to be log n, we can solve the problem very quickly. So we explore the more interesting case when this advice string is limited to be less than log n bits. And for this setting, we derive, again, both lower and upper bounds with a dependence on the number of bits allowed for the advice. And we explore both deterministic and randomized algorithms for the setting. And that's it. Thank you.